I've been a geologist for about 33 years now. Exploration geologist. I lived here for 13 years in Cal, and about 9 years ago I joined HiSeis to do seismic interpretation of hard rock seismic, hard rock being for minerals. I left there 2 years ago to start my own consultancy doing the same sort of thing because I wanted to keep going the direction I am going in, and it's working out quite well for me, so I'm very happy with that. And what I'm showing you tonight is how I interpret 2D seismic geology, 2D seismic, using all the data sets that are available to me. It's an integrated approach to an interpretation. I've found that I've seen a few people doing seismic interpretation by just drawing lines on the seismic data, and in the minerals industry that doesn't work very well. So let's get on with it. We can develop exploration targets using a multidisciplinary approach, and that's what we really want to be doing. We don't want to be spending our time just looking at one data set and saying we should drill here. We want to put everything together if we can. The scales that we're investigating are quite large with 2D seismic. We're generally looking down at least 1.5 kilometres. So it's not much good just looking at the tiny detail stuff in the top 100 metres, because you're going to get that out of your other data sets. We're going to be using every data set that we can, and in this case, magnetics and gravity and a few of the other potential field data sets are about the right sort of scale that we can integrate seismic data with. The challenge has always been resolving the geophysical information from 300 metres and deeper. The magnetics and the gravity and some of the other data sets tell us a lot about the top 300 metres, but how do we resolve good information at depth? Seismic, or reflection seismic in particular, is what I think is the best way to do it, because it retains its resolution as you go down. So at 1,000 metres or 2,000 metres, it's still going to have the good resolution that we want, and we can actually, with a 3D data set, I'm not really talking about 3D tonight, but a 3D data set, you can pinpoint drill targets to within a couple of metres. So it's actually very, very good. And I think the main thrust of what I'm talking about is that whenever you're doing a 2D interpretation or an interpretation of 2D data, 2D seismic data, we need to develop a 3D model as the result of that 2D interpretation. It's not we've got a 3D problem that we're dealing with. The seismic will image in all directions. It's not just directly below the seismic data, it's coming from everywhere. So the result of a 2D interpretation is a 3D model. Do people do Wordle? Yes. Has everybody done it today already? You haven't? If you, like those who are going to do it, I'm going to spoil it for you. Is that going to be a problem? All right.
You're showing off there with those scores, eh?
Yeah, so yeah, those sorts of numbers, that's not an accident. That's coming, the reason I've got this up there is because the approach I use to Wordle is pretty much the approach I use to everything. Get as much information as you can together first before you actually start trying to do an interpretation. Now your guesses are your interpretation. All right, so spoiler alert, if you are planning to do your Wordle, look away. So, my approach to doing Wordle is I start with letters that give me the best chance of success. So I gather information first that's got the most chance of giving me a result at the end of it. So yeah, I start with all the vowels and many of the letters that are going to show up in my words. Right, so with those two words, I get a really good head start. So I get many results of 3, and that's pretty unusual. So I went with gavel. That's a really weird word, but turns out to be a really good one because the next one was the answer, and that was bagel. Now, I wouldn't have got that in 4 if I had just gone with a random number or just gone with a first set of words that didn't give me the best chance of success. Now, my approach to doing seismic interpretation, he's going to get it in 1. Look at that. He's cheating. A bagel, it's like a donut that doesn't have sugar in it. So,
What's bagel?
Oh, there was two.
Cheese.
Yeah.
We got it 4 as well.
So the point of doing this is that you don't start doing interpretation with just one set of data. Like if I just had one letter up there, there's no chance of me getting the right thing next. So gather as much information as you can, and then start your interpretation with that. So the type of things that I'm talking about are magnetics and gravity. They're the most appropriate things that we're going to use for a seismic interpretation because they're about the right sort of scale. We want the gridded data if we can, not just the images, because those images have already been worked on by a geophysicist and they've made their own interpretation, or they bias the data when they put those side lighting things on. So if you can get the data, you can actually control your dynamic ranges and really focus in on the area you're most interested in. Mapping, of course, Trippy's good at this. Get the mapping done, get that mapping into your system so that you're referring to actual observed data, not just somebody's interpretation. Drilling, of course, drilling is observed data as well. That's your check on your interpretation. Drilling is the rotary light detector. You've got to make sure that the results you're seeing in your drilling correspond with your end result in your interpretation. One of the things that we rarely get for what I need to do is this sonic data here. So sonic data is information about how well the sound travels through the rock, and that's what seismic is looking at. So the full waveform sonic is what we really want, but if you can't get that, we have a handheld tool. Max came up with the term Crazy Ivan, and I like it. It's a Russian tool. You put it on the core, it works out what the velocity of that core is, so the sonic velocity of that core is. EM and other geophysics. Inversion models. So if you've got an inversion model, that can really help improve your model, your interpretation. Passive seismic's getting a bit of a run-in at the moment. There's some good marketing going on by Fleet Space. If you've got it, we can use it for doing the interpretation. Quite often there's government seismic data around the place. That government seismic data is a useful data set. It's free. You just have to bring it into your program and project. It doesn't have to be on your tenement to be useful. If it's a long strike, you're going to get information from it. And of course, your acquired seismic data, which means you hire Ultramag or Terex, go out there and gather the data and then put a proper interp together on that. If you just try and interpret 2D seismic data in isolation without having any of the other data, it's an exercise in futility. There's stuff coming from everywhere, you need to know where it's coming from. So what can we see with the seismic data? We can see lithology contacts, of course, which is what you're all used to seeing from the oil industry. That seismic data you saw at university, that looks fantastic. We don't get to see that, so don't get your hopes up. But what we do see that they don't see, we see alteration zones, we see mineralisation, we see faults, we see shears, we can see underground development. So if you've got underground development and you put a seismic line across the top of that, you're going to see where that is. And that can give you a depth control in a way that nothing else can. And some types of mineralisation will also show up in seismic data, like massive sulfides. You've got to expect off-plane events, and I'll explain them a bit later on, but things coming from away from the section of your seismic line. So here's your seismic line over here. Something over here can reflect onto that, and you'll image that, and it will show up under here because that's where your seismic line is depicted, but it's actually coming from over here. I'll talk about that a little bit further on, but be aware that they are going to show up in the minerals industry seismic data. Not so much in the oil industry because it's fairly flat, but anything that's dipping is going to give you some issues with off-plane events. So we start with the gravity. This is getting all the data together. I'm going to run through here a case study of Iceni Gold's deposit that we did. We did four 2D lines out there. They needed to unravel what was going on with the geology there. So the starting process for me is gathering a whole bunch of data together. So gravity, this is magnetics, and this is, when I say get the data, I can change the values that I see in this by changing the dynamic range. That's why I want the data. If you get an image, those are already set by somebody else. I like to be able to change it. some of you know that I used to do a lot of photography in Coolgardie. I've carried my photography stuff across into working in this, so I get the images that I want from the data itself that allow me to interpret stuff that a lot of people just don't see. So this is the project area that we're working on. This is radiometrics. Didn't tell us anything in the radiometrics. It's only the very shallow stuff, so not much point putting that in. Topography data is amazingly versatile, and it's an underutilized resource that's available to everybody. If you have a topo data, I've increased the vertical exaggeration by 10 here, but I can see where the faults are. There's another fault through here. Those show up in the topography data. So it's a free data set, grab it. If you've got LiDAR data, even better, but that's not free. Tomographic velocity modeling. This is working out the velocity of the rock in the ground as part of the seismic survey. This is analogous to what the ambient noise tomography that Fleet Space is selling, but this is much higher resolution. This has come directly from the seismic acquisition. It's basically working out the depth of weathering. So you can see here the weathering 3 times, 5 times vertical exaggeration on this. This is the top of fresh rock through here. So it's, it does really show the data very, very well. And we used that in this process, in this particular project. This is a gravity inversion. If you've got it, use it. We actually did a gravity inversion using that tomography data. And that really improved the gravity, which then improved my interpretation. Mapping, in this case, a lot of it's undercover, but we're still seeing some outcrop there. Yeah, it's away from the seismic data, but we're going to use that data anyway as part of the process of developing a 3D model. This is free, Google, just grab it. This is the tool, this Crazy Ivan tool that I talked about. Getting the handheld sonic measurements on the core gives us an indication of what the velocity of that rock is. We also measure the specific gravity of that rock. Those two properties together are, when they're multiplied, give us something called acoustic impedance. And reflection seismic sees changes in acoustic impedance. That's what we're going to image with a 2D seismic data set. So this is a very useful step. And if you can do that before doing the seismic survey, this is a good thing, right, Costa? It should be done before you even start doing a seismic survey. And if I had done that on the job that I'm talking about with Costa, we probably wouldn't have done the job. It showed us that we shouldn't have done it. This is the regional seismic data. This is a GA line up around Leonora. Goes from Leonora through Laverton out beyond. That's off the tenement, but you can use that sort of data to help work out what the global sort of, or the more regional structures are looking at. So the seismic data that we're looking at on this project. Now, as I mentioned, it looks nothing like what you're used to seeing in the oil industry. There's not a lot to see in this data by itself, which is why I said before, trying to interpret this in isolation is an exercise in futility, because you're all looking at that saying, I can't see a thing in that. And yeah, it's really hard to see something in that. Bring in all the other data sets and you'll start to see these things actually popping up, and they make a lot of sense. This model that I'm showing you now is holding up. They're actually testing it and it's finding gold. So although this looks like it's not much there, this was the key to unraveling the geological complexity in this project, and it's now producing gold for them. So this is the normal, this is pre-stack time migration, one of the processing runs. This is an attribute of that, basically an imaging process of it. So it's not the same, it is the same data, it's just sort of had a bit of trickery done to the image of it. But that can be a very useful set of tools as well, with changing the attributes. So we're going to start interpreting the data. For me, I'm very comfortable looking at magnetics. I can see a lot of stuff in the magnetics. I can't see as much in the seismic. So I'm going to start, in this case, I'm going to start on the magnetics and find where I think the faults are. And it doesn't have to be perfect. You just put a lot of lines on there that you think you can see, and I'm pretty happy I can see those throughout there. I don't know what the dips are, but that doesn't matter at this stage. I just want to know where I think there might be some faults. And then I put the seismic data on there. And so I start to compare seismic data versus those faults. And when you do that, it still doesn't look like much here because I've got a colour scale on there that isn't quite appropriate for what I'm about to do. I'm going to change it into black and white in a sec. But you get to this point here and you start to see things coming down like that. So there's a fault there that matches up with that. There's another fault there that matches up with this one. There's another fault here that comes down through here. Over here, these are a bit harder to see on this colour scale, but they are there. This one here is a major one. This is the Castlemaine fault out there. So we can start to see these things in the seismic data when you compare them with what we saw in the magnetic data. And that gives confidence to say, this thing here is probably real. Let's see if we can see it on the other sections. So these are the faults that I put together based on this particular project, these lines you're seeing up here. So I said colour scale on that was not terribly good colour scale. I like to look in black and white. I see a lot more. So these ones over here, they show up better in the black and white scale. And for the viewers at home, that's these ones over here. Now, whoops, push that button again. So, put the black and white image up there, and you can see that those are now starting to pop out when you turn them off and on. It's a bit of trickery there because you can see them now that I've shown you where they are. You can see them, but my experience is that these things turn out to be pretty real most of the time. Different colour scale, another colour scale. One of the things about doing interpretation is to look at different colour scales that are available to you and pull information out that's appropriate to those. So this particular colour scale is probably better for finding these reflectors. You can see some reflectors coming up through here and down depth here. This is 2 kilometres, not terribly useful for me, but I know there's 2 kilometres of reflection data coming out of it. This is one of those attributes that I talked about. This one's called pseudo relief, where it sort of highlights the high amplitude, the bright reflectors coming out. It also tends to highlight, in some cases, these faults, not so much on this particular thing, but those attributes can be a very useful tool for doing your interpretation. I do that in a free program, so I do that myself. The processing guys do this work. I do the attribute data in a program called OpenDetect. So it's free, may as well use it. So that's what we're looking at for these particular faults on this section. But here's another section here and another section here. And I was able to trace those ones through those data sets. So I'm pretty happy that they are holding up. Looking onto the one that runs north-south, what we're seeing on here is a big kick-ass reflection through there. Now, what does that reflection look like? What is it actually representing? I don't know at this stage. I can see something there. I can also see other things down through this area down through here, and these others that come in through here. A bit hard without the glasses on. So I'm not sure what they are yet. There's a bit of ambiguity in that data set, so I'm going to go back and have a look at those a bit later on. I know they're there. I'll have a look at them later on. Go back to the mapping. Now, mapping, depending on who does it, can tell you all sorts of different things, and it's best to have a look at, if you've got Trippier's data, use that. That's the best. Don't shake your head, it is. If you can get observation data, that's what you want. The interpretations are good, but that's somebody's interpretation. If you can get the actual observation points, where people have gone out and got information from those locations, you can then start to feed that into your data set. You're not looking at somebody's interpretation, you're looking at observations. So this is one person's mapping, this is another person's mapping, this is another person's mapping. They're all the same area, but you've got different versions. So it's good to get all of it, have a look at what you can pull out of each of them. There happens to be a bit of a shear here, and that was important. That turned out to be really important for me, for looking at what I'm looking at, for doing my interpretation. So by digitizing on that map where I think the contacts are, and then coming back to the magnetics and saying, well, I know that these things here are lithological contacts, they're not structural contacts, I'm going to put those in. But unfortunately, they hardly cross the seismic lines. So I'm going to have to start interpreting the data rather than just putting it in there and run with it. So I got into here and I can see, well, there's something that comes down through here and there's something that comes down through there, and those are the shears that were mapped. And this one here is not actually mapped, but it's a shear that's occupying a drainage system. So that matches up with something through there, and that one matches up there. Those two things I can say, well, they're probably faults now. And I've got something here that extends through, so the faults are pretty close to what the stratigraphy is. I'm not sure what's going on here at all. So it's time to start doing a little bit of collaboration with, in this case, Southern Geoscience. So this is a tomography data set, tells me what the top of fresh rock is. Top of fresh rock's a very useful product for feeding into a geophysical, a gravity inversion model. So the original inversion on this didn't have that constraint in there. We sent this to Southern Geoscience. They delivered a really good inversion model from this data set. This is my top of fresh rock. This is the inversion model that came back. Now, that matches up really well, that matches up really well. So we're starting to see that these things are actually supporting each other. It's supporting data. So I can then start to say, well, I think that this thing here is actually, it's not the top of fresh rock. That turns out to be a granite. So this is like quite slow. And then there's some heavy stuff underneath the granite. We've got a very thin layer of granite, which is that big magnetic thing that we saw. So then I'm starting to put in some structures into that, which are supported by the other data sets, in this case, gravity. And so now we're looking north on the other sections, and these things, we're seeing there's a zone up here that's got a different reflectivity. You can see there's a bit of a slight hint in the seismic through there that this is different to this. Out here, again, we're seeing something a bit different. Forget the edges. The edges on seismic are places to avoid because you're getting migration in there. Really stick with the zone through here. So again, we're seeing something coming in through here. That's sort of reflected in the gravity data set. But it implied we had this big, dense intrusive sitting out to the edge there. So does the drilling help? If we put the drilling on, in this case, this is a diamond hole that we had that they were trying to test for gold in this area. Well, yeah, when we put that inversion model with the drilling, there's a big, you can see in the drilling that there's something corresponding with that particular density. So it's all starting to come together in this data set. In here we see an altered granite and an unaltered but very highly magnetic granite down through here. And those are showing up in these strip logs. So you go out there and you get your MagSus. So this is MagSus. With that tool that I showed you before, we've got velocity. This is the P wave velocity, which is the compression wave. It's the fast one. And then we've got the SG values in here. And you can see that they're roughly corresponding in this case. And that, when you multiply that with that, you end up with acoustic impedance. Acoustic impedance is the thing that we're looking for. So we expect to see reflections coming from, do I put it in? So we have a couple of shears that have been logged in the data. And we expect to see reflections coming from there, there, and there. These are too slow, but that's a very strong, sharp change in acoustic impedance. Those sharp changes in acoustic impedance are the things that give us the reflections. And so this thing here is a shear with a bump in the acoustic impedance, and that's the thing that we're seeing in that seismic line. So here's that drill hole, here's the shear, here's where it shows up in the seismic line, which is this thing through here. It's not a strong response in there. This one's a stronger response here, but it means that you've got a couple of targets to chase up. So if we now go and look at the other end of it, these are those shears. I probably haven't shown it very well, but these are off-plane events. So these things, this thing here is the reflection from this. They're a little bit shallower. Anything that's pretty much horizontal in the goldfields, you can expect to see as an off-plane event, and I'll talk about them a bit more further on. to cover in that. But anything that's horizontal in your seismic line is probably an off-plane event that's running, that has the same strike as the acquisition line. So this is the end result of that interpretation of the 2D seismic data with all the other data sets. And they're finding gold on here, and they're finding gold out through here, but this is the main one they're testing right now. So the model is holding up. They've been going out there trying to kill the model, which is what I want them to do, and it's holding up really, really well. So they didn't know what was going on in this area. They had rough idea. The mapping sort of gave them a good idea. The seismic and pulling all the data together has integrated that into a model that they can now test. And that's the whole idea of doing this sort of work. We actually want to produce something that we can then target. So it's an excellent example of how grabbing all that data and interpreting it together can give you a result that is useful. It's one of the best examples of collaboration that I've seen between various companies. So the original company, Dave Nixon, now works out there. Many of you know Dave Nixon. He's now the exploration director out there. He had been gathering that sonic data on the holes anyway, so he understood the value of it. Ultramag did seismic and gravity acquisition on the 2D lines. Daybro Geophysical did the processing. They're a Queensland company, but they're able to do very good seismic processing, equivalent to anything I've seen from any of the hard rock seismic companies. Southern Geoscience did that inversion model, and of course I've put together the seismic design. I advised on the processing, and I did that interp that you saw there. So there's been a lot of talk about pegmatites. Everybody wants lithium these days. There isn't many good geophysical methods that I've seen that work all the time. Even seismic doesn't work all the time. But an example here from St George Mining up at Mount Alexander. We did this seismic survey looking for nickel massive sulfides. We thought this thing might have been a massive sulfide. They drilled it. Turned out that it was an interval with this interval here had 120 metres of pegmatite, but the whole thing was full of potential pegmatites in here. They're showing up in the drilling. So we were able to image pegmatites, turned out to be within a granite at 400 metres depth. So it works. This is the same line here. So this line here you're about to see is coming out of the page. This is that line. And this is what that seismic line looks like. This is what the pegmatite looks like in the other direction, which gives us this shaped thing. So putting together the seismic data and the drilling data in this case allowed us to produce a pretty big pegmatite. I don't know if it's got lithium in it, they haven't released those results yet, but it's a pegmatite that we've been able to model with one drill hole and some seismic data. And it's like 400 metres down below depth and below surface, and it doesn't daylight. There's no indication of this on the surface. So AI is the product of velocity and density. This pegmatite, the big one down here, is showing up because there's a big drop in velocity in there. Now they should have the same density, and they roughly do have the same density. What we're seeing here is a drop in velocity, and that's enough to give us a seismic reflection. We also have a bit of a structure. So this pegmatite's come in towards us in the middle of a structure. We're seeing the top of the pegmatite as a structure, a low velocity zone based on where the sound waves going through the rock get impeded by the fractures in the rock. So we see those faults as reflectors in this case. Now this is one of those strip logs where we've got velocity down here, and you can see down here that velocity dropped right off. Density was pretty much the same all the way down. This is the SG log, the blue one, pretty much the same all the way down. RQD sometimes gives us a response, not much RQD difference there. And so big change in acoustic impedance due almost entirely to the velocity change. This is a pegmatite in Coolgardie, Nepean. 400 metres of pegmatite through there. You can see there's a strong density change through there and a reasonable response in the velocity. And that gives us a strong response in the acoustic impedance throughout. Now, I should mention there isn't necessarily a response in the density from the velocity. I've seen a little bit of marketing from some of the passive seismic people saying that a drop in velocity equals a drop in density and corresponding increase. That's not the case. Velocity is not related directly to density in the hard rock field. It is in the oil industry where you get shales and sandstones. You'll see a change there and a relationship, but in metamorphic rocks like we've got, that relationship doesn't hold true necessarily. Sometimes it does. You can't predict it though. I'll flick through these. This is the seismic section from there. Now, HiSeis had collected this data. The company asked me to get it reprocessed and interpret, so we've done a reprocessing. This thing here is an off-plane event. It appears to be sitting in the middle of the pegmatite, but what we're seeing there is a reflection from 800 metres away, a big granite pluton that dips back towards the seismic line. We're seeing a reflection from that granite pluton, and it's showing up here, even though, sorry, it's out over here somewhere. All right, so you can't, when you look at 2D seismic data, you can't expect it to be looking directly below, and it almost never does. So one of the things that I'm always asked is, how do we find pegmatites? Because I don't just do seismic, I sort of help a lot of people look for a lot of stuff as an exploration geologist. And the problem has always been for pegmatites, what geophysical method works. Now, ground probing radar works to some extent, off and on. Phil likes to talk about it. Phil's from Ultramag, I should say, Ultramag. They do ground probing radar and it works. It gives a lot of false positives, but it also tells you where they might be. So that's a good thing. Turns out the seismic can see it as well. So if you're not sure where these things are or if they're big enough, seismic can work. It's not always going to work. Do tests first before you think about it. Anyway, as long as they're more than about 30 metres thick, we're likely to see them. So I'll just flick through these. This is Alicia's husband's project at Ozoran, just near Karasu Dam. We had the magnetics. We had some seismic that was collected by Saracen on the ground near Karasu, on Ozoran's data, Ozoran's ground. That's the seismic data. Doesn't look like much, but when we combine it with the magnetics and what the company already knew from their work, we ended up with a fault network that looked like that and a model that looked like this, using all the magnetics, the seismic data, all the other information. So we started with not much, ended up with a pretty robust model. It's holding up okay at the moment. Andrew's pretty happy with it, so it's good. As long as I've got happy clients, I'm a happy person. This is Mount Alexander. This is the stuff we saw before. As I said, we weren't looking for that. What we were looking for was nickel sulfides. Yes, out here, but anywhere in their tenement package. So we grabbed the magnetics, and this is the model that I ended up making from the magnetics and the seismic data. The things that we're seeing way down here in the seismic are coming from over here in the real world. So we could end up making a really big model. They wanted to know what these faults were doing. We could image those in the seismic data. This is kin mining. We started with the magnetics, a bit of an interpretation on the magnetics, just looking at where the faults were and where the lithologies were. We put in 3 seismic lines into it and looked at all the drilling data as well and ended up with a geological model that does that. So that becomes an exploration model that they can now test. This is almost direct detection stuff. This is paleochannel uranium in South Australia. Yes, there was some tremino done over the area, a lot of tremino, and this is probably the place where I've seen it best used. They were looking for the paleochannels. They could find the paleochannels. A few false hits because tremino only shows you where the strongest reflector is. If it's in a paleochannel, that's great, but it also shows you top of weathering. Top of fresh rock. So you can't tell directly from it whether it's top of fresh rock or paleochannel. But for these guys, what they needed to see was where that uranium was. And the seismic, the reflection seismic data, was able to pull out the horizons that contained uranium in this deposit. So they put a lot of drilling in, but if they'd done the seismic first, they wouldn't have had to use so much drilling. And this is a very good set. This is from Ultramag collected this data set using the little eVibe. We're seeing down 3 kilometres, 4 kilometres down here. This is what we needed to see though. So what, from these 6 lines and the magnetics, a intrusion model was developed, which is now helping them explore for nickel sulfides at carboid rocks. So they're now looking for along the base of the basal contact of this intrusion. Now, I have mentioned a little bit about off-plane events. This Kanowna Belle data set was collected when I was working at Kanowna Belle. I had no idea about seismic at the time, and neither did anybody else, including the people who put the program together, apparently. Because if they had understood off-plane events, they wouldn't have put these lines where they did put them. So, Kanowna Belle has Fitzroy Fault through here. Unfortunately, Northern Star wouldn't share the model with me. I had to make a model up based on publicly available data sets and memory from having worked there. So, Fitzroy Fault's out here. We've got Grave Dam grits, and we've got the Kanowna Porphyry, and there's an ultramafic over here as well. And it's dipping, the whole thing's plunging to the south on this. And we're looking for basically the Fitzroy Fault as a reflector. And this was the data that we got back from it. And we're thinking, oh yeah, that looks interesting, but it's in the wrong spot. So here's our seismic line out here. Kanowna Belle Mines there, we had a seismic line out here. We were expecting to see the Fitzroy Fault at depth. That's what we wanted to see. How far down does it go? The curse of the off-plane events really mucked us up. So here's my model. Come back to this one here. And so we had a reflector up here that had the same sort of shape as the Fitzroy Fault. But this was 1,250 metres down and this is 750 metres down. So obviously this seismic stuff doesn't work at all. It's wrong. It's in the wrong spot. So we just put it aside and didn't do anything with it. Northern Star came back to us when I was at High Size and said, can you reprocess the data? Can we do anything with it? So I do forward modelling. Part of my job for interpretation is make a forward model of the model to see what response we're going to get from the geology. This is a geometric forward model. It shows me that we should expect to see the Fitzroy Fault up here. And look, the forward model shows exactly what we expected to see. So why didn't we pick that up at the time? Well, it turns out that what we need to do is imagine that we are imaging perpendicular to the reflector. And that these rays here are where we would see the Fitzroy Fault from this 2D line. And this is the part of the Fitzroy Fault that we are imaging. It's an illumination model of the Fitzroy Fault. And so what we do is we rotate the seismic section back up to reinstate the assumption of 2D seismic, which is that it's perpendicular. So by doing that, and then looking down on it, you can see that, look, it's actually matched up really, really well. So what we're seeing in the seismic data was actually real. The Grave Dam grits are these things coming down through here. The porphyry's up through here. There's an ultramafic out through here. Had we known it, we would have explored for velvet over here at the stage. We didn't know velvet was there. I put a drill hole into it. Oh shit, when was it, Jared? Do you remember velvet? It's about 2005, 2004? Something around there. We would have, if we'd known the seismic data, if we'd understood this principle of reinstating the 2D assumption, we would have hit that much earlier. It was just, I drilled that hole thinking, we haven't drilled out there, let's see what's out there. Turned out to be velvet and, you know, a lot of gold. This is the forward model in that same area. So it's doing what we expect it to do. At the time though, we looked at this, oops, going the wrong way, sorry about that. we looked at this 2D data set and thought, no, this is bullshit. It's just not working. It turns out that it did work very well. Nobody understood the implications of off-plane events. So when you look at 2D data, don't expect 2D seismic data to image directly below here. It could be coming from anywhere. So the best way to overcome that is survey design. Yeah, you put your line in here, but you also put one across it. Because if we'd put one perpendicular to that, we would have seen that these things were dipping, plunging at 60 degrees or more in that direction. So ideally, you put a dip direction line and a strike direction line in, or perpendicular to the dip direction. That's how you should design your 2D seismic data sets. So think of 2D seismic data as representing distance, not depth. It's a distance away from the seismic acquisition line, not a depth below it. It's incapable of imaging or letting you know which direction it's come from. It's like sticking your finger in your ear. You can hear a sound, but you can't tell where that sound's come from. And so yes, the only true way to do it is to resolve that is to do a 3D seismic survey. And that's a big outlay. And for many companies, it's actually worth doing because with a 3D seismic survey, you can plan your drilling on that survey. It's amazing how well it works. But intelligent interpretation of 2D seismic data by integrating all the data sets that you have available can give you a very valid model to work with. It's an exploration model. It's not necessarily a drill targeting model, but it lets you know where you should be looking next. It's a cost-effective proposition too, because 2D seismic data is not that expensive to collect these days. Companies like Ultramag are out there collecting data for between $6,000 and $8,000 per line kilometre, and that's under half the competition price. So it's not as expensive as it used to be. But I would always recommend de-risking. Make sure that you will see what you expect to see by using your full waveform sonic tool down the hole or using that handheld tool on your core in the core yard. All right. Thank you very much.